Hello everyone, this is Shen from Wenzhou Kean University, Wenzhou, China. Today it's a great honor for me to present my paper at the WCB 2022 workshop. My paper title is Semantic-Guided Zero-Shot Learning for Low-Light Image and Video Enhancement. Dr. Gaurav Gupta is the supervisor for this project. Here's a brief outline for my paper. First, let's talk about the challenges with low-light images. From the following figure, we can see my proposed methods had the best performance in terms of color, contrast, illumination, and edge information. In comparison, other methods either fail to reach the dark regions or generate unpleasant noise or blurs. As we can see from the previous slides, low-light images tend to have degraded feature contrast, which lead to poor low-level perceptual quality and substandard performances for high-level tasks, such as object detection and semantic segmentation. In early years, people tend to choose camera or software side to address the low-light image problem. However, camera will inevitably introduce noise or motion blur, where software usually requires high artistic skills and are also inefficient at diverse illumination and large-scale dataset. The conventional methods algorithms can be roughly divided into histogram acquisition and Retina theory. However, both approaches require manually selected priors. They also require a complex computational expensive optimization process. As a result, they are unsuitable for real-time processing. Since 2017, deep learning methods have made great breakthroughs in image enhancement. The supervised methods rely heavily on labeled training images, whereas the unsupervised methods and zero-shot learning method eliminate the data bias problem. However, all these methods ignore the semantic details, which is important for high-level tasks such as detection and segmentation. To address the issue, we tend to design a completely new model architecture comprised of three modules, including enhancement effective extraction, recurrent image enhancement, and unsupervised semantic segmentation. Here, we have a low-light image. It will go into the enhancement factor extraction network and output the enhancement factor map, which records the pixel-wise light efficiency for this image. So here, we have the recurrent image enhancement network. The recurrent image enhancement network will receive both the enhancement factor and the low-light image. In this recurrent process, the previous stage, the output, will be used as the next stage input. Finally, we have the unsupervised semantic segmentation network to help us maintain the semantic details using a semantic loss. Here's a visual demonstration for the enhancement factor extraction. As we can see, the left column is the low-light image, and right column is corresponding enhancement factor map. Here we use darker regions to indicate low values for the enhancement factor. Let's take this bright sky as an example. So this region is much brighter than the other regions. Therefore, we want less enhancement and therefore lower values in the enhancement factor here. And these rows are obviously darker than the other regions. So in return, we want more enhancements, therefore larger values for the enhancement factor here. In this way, we can achieve the enhancement for one image with mixed overexposure and underexposure regions. Next is our recurrent image enhancement process. Here we use xt for the pixel values in the t stage, xt-1 for the pixel values in the t-1 stage. xr is the enhancement factor and order is a hyperparameter. According to this figure, when the order equals true here, we have the most robust image enhancement. Finally, let's talk about the loss functions. We have the spatial consistency loss to guarantee the spatial coherence between the low-light image and the corresponding enhanced image. So for this part, we consider the 8 adjacent pixel regions. And for this part, we're considering the non-adjacent pixel regions, but with alpha to adjust the importance. Next, we have the RGB loss, which tend to balance the red channel, green channel, and blue channel. Third, we have the brightness loss to adjust the exposure level using this hyperparameter E. Fourth, we have the TV loss. Finally, we have the semantic loss to accompany the semantic segmentation network. For these implementation details for the paper, our implementations includes around 2,000 training images. It took approximately 3 hours to converge on single GPU. These are the evaluation datasets, including several benchmark datasets, and 2 are our proposed dataset. This is the ablation study for this paper. You can check more details and other ablations in the manuscript. Here we will only show one visual ablation. The visual ablation shows all introduced loss functions are crucial for state-of-the-art enhancement performances. We also make quantitative comparisons with other state-of-the-art models. And we can see in terms of both runtime, parameters, flops, or user study score, our model is substantially better than others. We also show quantitative comparisons on other scores such as PSI, SIM, unique, and Briscoe on both inside and real-world low-light images. As we can see on the most challenging large-scale dark cityscape, our method had the best score. On LOL, our method has the second best score. And for this benchmark dataset, our method has the best overall unique score and the second best overall Briscoe score. Here's a qualitative comparison on the VV dataset. We show our method has the best performances in terms of image enhancement and facial detail preservation. We also test our model on low light detection. As we can see, our methods help the ULO detection algorithm detect the most amount of colors in night regions. Finally, we show the low light semantic segmentation performances using PSPNet as a segmentation network. And we can see our semantic segmentation results is closest to the ground truth compared with other models. So in conclusion, in this paper we have proposed a semantic-guided zero-shot low-light image enhancement network. Our model comprises our enhancement fact structure network, a recurrent image enhancement network, and unsupervised semantic segmentation network with 5 non-reference loss functions. In this way, our method is trainable with no pair images, unpaired dataset, or segmentation labels. One major contribution of this paper is that for the first time, we combine low-level enhancement with high-level semantics. Comprehensive experiments show our method is efficient and effective. In the future, we hope to explore more about motion blur and mirror reflection in low-light conditions. Thank you.